So this is just my dump on collision, non-collision theory on kinetics, which we're going to start with collision theory. So the first thing that has to happen for a reaction to happen is there has to be the particles that need to come together. They must hit. They don't come in contact, and they can't react. They must have enough energy to go over that activation energy. So you have to have enough energy to get to that intermediate so you can go over the boundary. And then depending on the substance, they might need to be aligned correctly. So maybe this needs to hit there and not over here in order for the reaction to happen. So if you increase the concentration, then you have more particles, and so there could be more reactions and they would happen faster. Or if you increase the pressure, once again there's more particles, so it's going to be faster. If you increase the temperature, that changes the Boltzmann distribution from that to that, so that you have more particles moving faster. And if this is our energy of activation, there's more particles over here now, and so not only are there more collisions, there's also more particles that have that activation energy. If you increase the volume, you're going to spread things out, and so you'd end up with lower reaction. So those are things to think about. You've seen this. You should understand that this is an exothermic reaction. That's an endothermic reaction. Just like you've seen this Maxwell-Boltzmann distribution, and you should understand it. But we should also know that if we lower that barrier, we're going to have more particles they can get over, the same with adding temperature. But when we lower this barrier, normally what we've done is added a catalyst, and catalysts can work in a whole bunch of different ways, but they give you a different mechanism in order to get to the products. And so normally a lot of times what they do is they arrange the orientation so that, if I put all these gas particles and they stick to the surface like this, then the only side you can really hit is this end. So if we have that other particle coming along, it's always going to hit pretty much there if it hits and not hit on the end. So you should know what a catalyst is. You should know it speeds up a reaction. These things called inhibitors, they slow down reactions, they raise the activation energy, and so maybe they make it so the particles on the surface are always like this, and so it's hard to hit that side, so they slow down the reaction. Sometimes we want to speed up reactions, and then when we're dealing with food, we normally want to slow down because we'd like that food not to go away and spoil quickly. We should know that rates of reactions are correlated because we have this thing called a balanced chemical equation. Is that balanced? That's balanced. Okay, so let's write the rate for H2. It's going to be equal to just the change in concentration of hydrogen over the change in time. It should be a little t. And that's just what the rate is. And then, these rates, since they're in a balanced chemical equations, are all going to be related. So delta H2, so hydrogen over time, is going to be related to the change in nitrogen in time, but they're not going to be the same, because for every one of these I'm going to use 3 of these, and so for every 3 of these I'm going to use 1 of those. In other words, the nitrogen is going to be used up 1/3 as fast as the hydrogen. And then we can go and we can say that the ammonia is made at 2/3. These are being used and this one's being made, so it's going to be a negative. They're going to be the opposite sign. And so all these rates are related. Or you could write it in terms of a different one. Let's say we do the rate of N2, it's just the change in nitrogen over the change in time. That's going to be a negative number because we're going to use it up because it's a reactant. Equal 3 times the rate of hydrogen being used and 2 times 3 to NH3 that is formed. And so that's what that is. And then a lot of times we just talk about the rate of reaction. And that's always a positive number. If you have one with a coefficient of 1 in front of it, you can just use that one. As I said, it's always positive, so you need to make sure if it's a negative value, if it's a reactant, you put a negative sign out there. If they didn't happen to have all ones, then hey, from the step above, we would know the rate of the reaction is 3 times that of hydrogen, because that's what it would be if there's a coefficient of 1. Rate of reaction, we talked about that. Let's see. Next thing we would do is we could find a rate equation. I don't like that. So we have rate laws, and they look something like rate equals K, that's a little K, A to some power, B to some power. And we always get these things from some type of experiment. So a lot of times what they do is they give us a little table, plus concentration of A, concentration of B. They have some type of rate. And this one is going to be molarity per second. They tell us the concentrations in molarity. And they give us some numbers for experiment 1, for experiment 2, for experiment 3. And you hope they set up the experiment nicely. Sometimes they do, and sometimes they don't. And forth. And then we should be able to come up with the rate law, or the rate equation for it. So rate equals K. We want to find what X is. So I'm looking for somewhere where A changes and B doesn't. If there's not that, then I might have to do a little bit more math. Oopsie, let's make sure I write down the numbers right. When I doubled the concentration and kept the concentration of B the same, I saw that the rate doubled. So A is first order. You don't have to write the one I normally wouldn't. And then B, we want to go find, let's see, in experiment 1 and 3, we kept those the same. When we went from 0.1 to 0.2, we doubled, and then we see that, oh, that's the hard one, so we need to get these to the same power. So this is really like 10 times 10 to the negative fourth. We quadrupled the rate, we doubled the concentration, so that's the 2. And then we can go and solve for K. We choose a reaction, or an experiment 1, 2, or 3. We plug in our numbers. K is what we're looking for. A was 0.10, B was 0.20. I squared that. I solved for K by doing my algebra, and I get 0.25. And then it's important to know units. So our rate was in molarity per second. This is in molarity. That's in molarity. So I get molarity cubed over here. I have 1 over molarity squared seconds. And I could rewrite my rate law, including the K. And that's a common question that you have to do. You should know that the order of the reaction in terms of A is first, in order in terms of B is second, and overall it's third. And then we have a few different equations you should know. So what we do a lot of times is we plot graphs, and we normally start with the concentration versus time. And if it was zero order, it would look like that. But normally they look something like that, and we have to figure out if they're first or second order. So what we'd do is we'd go make an ln of a versus t, and 1 over a versus t. And if this one was a straight line, then we know it's first. And if this one was a straight line, we know it's second. That would tell us the order of reaction with terms of a. And that's another way we can get it. We can also use the slope to find k. So we take the absolute value of the slope. Absolute value of the slope. And that would give us k. And then we actually have equations that tie into this one. So this is ln of a minus the ln of a naught equals negative kt. And so that's why that graph's straight. And then we might have to use that equation. So that equation could be helpful if we knew our starting concentration and we knew k and we knew our time, that we could find our final concentration. And I should talk a little bit more about that. If you need help with undoing logs, I'd be happy to show you that. And then we know that the first order reaction always has a constant half-life, and so t half equals square root of 2 or ln of 2 over the k, and so that's 0.693 over k. So if you're given the half-life, you can find k, and you have k, you can find the half-life, and that's given on your equation sheet. And then we'd have similar equation over here for, that's where your knot is, not there. And this one's positive for k because the slope's positive, but same type of thing. That's why that graph's straight. And if they gave you the initial concentration or the final concentration and the k and the t, you could find the other one. And so those are useful ways. Those equations can be helpful. That's the major things on kinetics. If you have questions, please let me know tomorrow. And we'll end there.